If you've ever played around with a spirograph or just seen curves generated from polar equations, you'll be familiar with a particular class of shapes that can be created this way, that range from something as analytically simple as a cardioid all the way to elaborate colorful mandalas like this one. These feel like they live in a world totally separate from regular Cartesian graphs, as those shapes never form loops or intersect themselves. But we can bring them with us into a place where both types of graphs make sense, and along the way learn how to extend the concept of derivatives to complex valued functions. I hope you enjoy. This is a cardioid. It lives in a polar coordinate system where this is the origin and this is the direction from which angles are measured counterclockwise. The equation that defines it is r equals 1 minus cosine theta, where r is the distance from the origin and theta is that angle we just described. Since r is linear, we might as well write that equation as r of theta equals 1 minus cosine theta and make it a function. But if we wrote that same expression using f and x instead of r and theta, you'd naturally expect this shape to be drawn instead. That's simply a matter of convention. R and f are equal to each other, and that also implies that their derivatives are equal. R prime is equal to f prime. But what we usually visually mean when we're taking a derivative of a function, that it gives us the slope of the tangent line that touches the curve at a given point, only applies to the graphic on the right. If we wanted to get a derivative that behaves the same way along a cardioid, the standard approach would be to convert it into a pair of parametric functions, one for each Cartesian coordinate, and then differentiate their ratio, like this. The algebra required gets a bit hairy in the in-between steps before it simplifies. I'm not going to go into details though, because this method is not what we'll be pursuing today. I left a resource in the description where you can learn more about it. What if we didn't have to mangle and split the polar form expression to find a meaningful derivative for the shape it creates? What if we could only adjust it slightly, take the derivative the regular way, and get all the same information the approach we skipped would have given us, actually even more? We need something that seamlessly integrates polar and Cartesian coordinates into a common algebra, and complex numbers offer themselves as natural providers of this service. We can write them either like this, or like this, and the polar form of complex numbers works exactly the same way as the polar form we use to draw the cardioid. That means that if we can find a way to express our cardioid as a continuous collection of complex values forming a shape in the complex plane, we can keep both polar and Cartesian aspects of it present at the same time. We can have our cake and eat it too. So how do we get the cardioid in here, algebraically, starting from this polar form? We start from the polar form for a generic complex number, r times e to I theta, and then we replace r with the expression from our polar form above. This lets us treat z as a function of theta, and as long as we limit the domain or input of this function to be real numbers, and consider its range or output to be complex numbers, we have successfully imported the cardioid into the complex plane. In this form, it becomes easy to both move the shape around and rotate it without doing any more conversions. To rotate it, we subtract some angle from theta in the part of the expression we got from the polar form, like this. And to shift it, we add a complex number to the whole thing, like this. It's the best of both worlds in one form. But it's important to note that after we shifted the shape, the input variable theta no longer corresponds to the angle of the complex number we get for that value. This form in general isn't mapping angles of numbers to their Cartesian coordinates, it's mapping some free real parameter to a two-dimensional complex number that is already fully defined without a need to specify an angle separately. This plot is parametric in the sense that the input isn't mapped to anything on the drawing, instead the drawing is described only by the output. To reflect that fact, let's replace theta with a regular letter t, as is conventional for parametric expressions, and restore the cardioid in the expression back to the simple form without any offsets. We can take a derivative of this function like we would of any other. No special rules apply just because the range has been extended to complex numbers. This is what we get. It's another function that also goes from real to complex numbers, so its output can also be drawn parametrically onto the complex plane just like the original. Let's do that. We now have a system where the form describing the original shape and the form describing the derivative are the same kind of mathematical object, a function that maps real to complex values, and we draw the original and the derivative using the same set of rules. It's just like what we're used to with real functions. But how are those shapes related to each other? How is the shape we're seeing now informing us about the behavior of the cardioid? The link is even more visually direct than what we're used to with regular derivatives, but to understand it, we need to take a step back and remember a few things about what regular derivatives are telling us. When we say that a derivative tracks the rate of change of a function, there is something implied here that is not often explicitly stated. It expresses this rate at which the output grows relative to the rate at which the input is fed into the function. The rate of 1 means that the output of the function gains exactly as much value as the input does. Between 0 and 1 means the output grows slower than the input, larger than 1 that it's faster, and negative that it goes down as the input progresses. The slope that we normally observe is not an intrinsic property of the function or its derivative. It's instead a consequence of graphing the function with its output orthogonal to its input. The visual direction we get from it, the one that describes where the graph is headed as input is fed into it, is a combination of those rates of input and output. This may feel like a bit of a moot point because under normal circumstances, the rate of input is fixed to be 1 everywhere, which has the effect of hiding the relative nature of what the derivative is communicating. But if the input was, for whatever reason, coming in at some other rate, the derivative would still tell us what rate to expect from the output relative to it. We can even change the direction by setting a negative rate of input. This relative nature will become important later in the video. For now, let's apply what we've learned to polar curves drawn on the complex plane. We'll use a slightly more elaborate polar curve for this purpose to make things more interesting. Given this polar expression, we get a curve shaped like a butterfly. We can import it into the complex plane the same way we did for the cardioid, by simply multiplying the whole expression with e to it, where t is our parametric input variable. We are feeding the function from an input space of t ranging from 0 to 2 pi. When the input is at 0, the output will be here. As we move it, the output traces the shape. Remember, the input space is not present in the complex plane. This means that a direction along the curve now has nothing to do with the input. It is entirely a property of the output. Luckily, the derivative of function z yields complex numbers, which are two-dimensional, so we get the full information about where the curve is heading from just one number. Its value at the beginning and the end of the curve, so at t values of 0, 2 pi, and at every complete cycle of 2 pi length, comes out as 3i. We can draw that as an arrow that originates at the output point we're inspecting, going straight up for 3 units. And let's also draw the shape the derivative, z prime, traces in another complex plane. For that we need to zoom out because that shape is a bit bigger. Funny enough, this also looks like some kind of insect, but let's stay focused. At input value t equals 0, the value of 3i we found earlier appears here, and we can show this complex number as an arrow that starts from the origin. That is the same arrow we've just seen on the butterfly. If we now move forward in input space, we can see how the complex values on the right form the direction in which the butterfly curve is evolving on the left. Alright, we'll watch it one more time, and this time pay attention to the varying speed at which the arrow is moving on the left. It's almost like a racing car going around a track. It slows down before sharp turns and speeds up in straightaways. And the length of the arrow corresponds to the speed at which it's moving. Speed and direction, what's that called again? Yeah, velocity. We got a bit of physics sneaking into our math. It's not really a vector here though, we'll touch on that again a bit later. There's even a hint of momentum in the system. Remember how the arrow shrinks and slows down near sharp turns? Watch what happens in the derivative space if we start here, approach the sharp turn, and cross through it. The arrow on the right approaches the origin, from where it has easier access to directions that are significantly different to the one it came from. Let's look at that again. What this tells us is that in order to make a really sharp turn, to quickly change the direction to nearly the opposite of where it came from, the head of the arrow in the derivative space needs to make it across the plane, therefore passing near the origin. If it took the long way around, like it does here for example, that would mean more time spent moving in a similar direction, resulting in a smoother turn. This begs the question, what is this time-like resource the curve is consuming as it's being drawn? Why does it matter? Couldn't we just get the same shape through a collection of directions that all have the same speed? Why does this imagined stylus we're drawing with have these physical properties? To answer that question, let's focus on the butterfly itself and the input space associated with it. The input space here is drawn to scale with the units on the complex plane. A length of 2 pi on the screen is the same for both. The first thing we should notice is that the line representing the input space is significantly shorter than the length of the curve describing the butterfly. This means that if we simultaneously run along the input space and the output space, we need to run along the butterfly faster to complete the cycle in the same amount of time. That explains why the arrows we were looking at and the whole shape in the derivative space were so big. This function produces more output than it consumes input. Both input and output are continuous, of course, but we can in a way imagine there are different densities along the shape of the butterfly. Let's make them visible. We'll hide the coordinate system and use the whole screen for that. This is the form we get if we imagine the speed at which we've pulled the stencil decides how much ink is deposited at each section. It's thicker where we slow down and thinner where we speed up. But for purely aesthetic reasons, I also want to show you what it looks like when we do the opposite. That is, faster sections appear thicker than the slower sections, and sharp turns disappear, a sort of calligraphic way of drawing. At this point, we're not really talking about math anymore, we're just smelling some flowers along the way. Thanks for joining me in doing that. Now let's get back to work. A story of complex derivatives wouldn't be complete without talking about functions with complex domains, so those where input can also be a complex number. Let's think about the challenge we're faced with here. We've seen that the idea of a derivative depends on some process that continuously feeds input into a function to give us information about the velocity of the output as that happens. That makes perfect sense when the input is real, because we can pick any number within them and then continuously feed numbers that come after it. But when the input is complex, we're kind of stuck right after we pick a starting number. There's all this space in front and behind it, in fact all the way around it. In what order should we be going through them and feeding them into the function? Complex numbers are not ordered. There is no notion of greater than and less than among them, which makes our challenge look a bit daunting, but luckily there's a catch. Maybe you noticed, as I was saying there are numbers in front and behind the number we pick, before I told you about the around part, that this is also true in a simpler way for real numbers. There are also numbers in front and behind them, so you might think, wait, there's also this ambiguity of direction in the reals. Why is that not a problem there? That little fact is a clue to tackling the infinite abundance of directions within complex numbers. Let's first deal with just the positive and negative directions in the reals, and we'll extend from there. What if we went back to our butterfly and fed the input range between 0 and 2 pi into it, but backwards? Naturally, we'd see the butterfly get drawn the other way around. What about the velocities? Same thing. The lengths of the arrows from each point would be the same as if we were going in the original direction, just pointing in the opposite direction. This is not a coincidence. Flipping the arrow is really all we need to do to get the correct velocity for the case where the input is being fed in at the standard speed of 1 in a negative direction. We've seen this when we've talked about derivatives of real functions being relative, specifically the case where the rate of input was set to -1. For functions with real inputs, we could basically pick any real number as the rate of input and use it as a multiplier that corrects the rate of output given by the derivative. For functions with complex inputs, we can choose any complex number as the rate of input, and the same will be true. And we'll probably want to express that complex number in polar form because we're interested in seeing the speed and the direction. But what does it mean, algebraically, to feed input in at a different rate? To show this, I'm going to declare a variable to stand for our rate of input, or velocity as we're interpreting it, and name it v sub I. We set that variable to be our polar form complex number. Now we first write a function taking input at the rate of v sub I like this. And that's what we take the derivative of, which by the chain rule is equal to the derivative of the inside, that comes out as just v sub I, multiplied by the derivative of the outside, the function itself, with the argument left as is. If we express the same thing in Leibniz notation, it looks like this. Notably, neither right-hand side looks like what we have here. To fix that, we're going to declare another variable, we'll call it x sub 0, and set it equal to v sub I times x. That is the input point at which we are evaluating the derivative. And now we substitute that into the Leibniz form equality, but only on the right-hand side. Okay, the argument of the function is the same as the variable being differentiated against, which makes this just a normal derivative, so let's replace that with the f prime notation. Now this thing we have on the left is called a directional derivative. A derivative specifically for a chosen direction expressed by v sub I. And that can also be written in f prime notation like this. To top it off, let's also give the rate of output a variable with a fitting name, v sub O, and set the expression equal to it. Once we're here, we can rename the variables in this expression to anything we want, as long as we do it everywhere. So let's do it to match the way we express the parametric function describing the butterfly. So we've gone a really long way around to just restate that a derivative is a ratio between the rate of change in output and the rate of change in input. But now we know that both of these are flexible, and when the function accepts and produces complex numbers, both of these act as velocities. As I say this, I feel tempted to pop arrows on top of them and call them vectors. But if I did that, none of these equalities would be true anymore. And I don't just mean that in some overly pedantic sense. This here is the most glaring problem. Even if everything else somehow made sense, we still could not divide vectors. So yes, we have proper velocities, but they are not proper vectors. And as much as I'm eager to tell you more about the way these definitions flirt with one another, that's going to have to be a topic for another day. What does this mean visually? It means that if we were to pick a point that we arrived to at the velocity of real 1, and took a turn in the input space before we went on, the output would make that same turn. This direction is of course valid only at the very start of our journey in this new direction, and is free to change immediately after it. In our case, it very quickly turns around and zips away. That works the other way around too. If we wanted to know which way to move in the input in order to get a nearby point in some direction in the output, we just turn this formula around. It's like a local inverse of the function. This expression is exactly true for velocities at a single point, but if we actually want to move in the output space by some amount by using this property, it will only work when our move is as tiny as possible. Basically, it's only exact at the limit as the distance traveled approaches 0. So if we take our usual input range between 0 and 2 pi and lift it just a tiny amount into imaginary space by adding a small imaginary number to it, we'll get an almost identical shape tracing the outline from the inside. If we increase this imaginary number, at every step of the way we'll be tracing close to the previous shape, but the differences in the outline will add up. Eventually we see outlines crossing over themselves and even escaping outside the original shape. Let's draw them again together. We can see now that the body of the butterfly is completely filled, so if we did this continuously, we would indeed have produced every point inside the butterfly at least once. There's more than one way to reach a specific output point, and we will not necessarily arrive at it with the same speed. It depends where we came from. But there are some specifically interesting points, namely near the tips of the wings, where we get this bunching up effect. The lines coming closely together, and those that come very near it, making very sharp turns. That doesn't mean any line passing through here will do this, but at least the ones we pulled from a sufficiently close input neighborhood will. You can see a good counterexample here, where the body of the butterfly meets the wings. We have these outside lines of small curvature slicing right through this area of high curvature, so they obviously don't arrive here at the same speed. To see a similar bunching up phenomenon for this area, we would need to draw some lines on the outside by taking the input in the negative imaginary direction, like this. And when we do that, we also discover similar points on the outside middle of the wings. Altogether, it looks like this. You know what? We have one spatial dimension to spare. Let's assign it to this imaginary offset we've been using, and we can see a 3D interpretation of this shape. Thank you so much for watching. I hope you enjoyed and learned something new. The trick we've applied here to import a polar curve into the complex plane also works in a similar way for regular graphs in Cartesian coordinates, and I've made a video about that too, Secret Kinks of Elementary Functions. Please share this video if you liked it and know someone who would enjoy it too. It helps my channel grow. That's it for today. See you in the next exploration. Bye!